potential energy. Good times? You bet. So, we know about work, we've been studying that, and potential energy, we know about spring potential energy and gravitational potential energy, but we haven't talked specifically about how we can turn any form of work into any form of potential energy. We just looked at a couple of specific types. We'll walk through those types to make a generalization about how work and potential energy are related. Sorry about the PowerPoint. I'd rather have written it out, but actually it's kind of neater this way. Lifting a block. Well, if we lift a block, we do work on it. We do positive work. We have to lift upward with a force at least equal to the force of the gravity on the block, if not more, if we want it to accelerate. And that has to be in a positive displacement. So we do positive work on it. When we do that, GPE increases, which is a wonderful thing. And it makes sense because remember the equation is mgh. So mass times acceleration due to gravity times height. It's going to lift it up. Good times for everybody. But if we look at the work done by gravity on the block, not by us, but by gravity, because remember that's the force that's going to provide GPE. Well, we didn't get something for nothing. Remember, energy can't be created or destroyed and all that. We have work equals mass times acceleration due to gravity. That's the force, which, as long as we stay close to the Earth, is relatively constant, times the displacement that it goes, the distance. Well, that's the same as mgh in terms of the actual numbers. But if we look at the signs, it is different. mg is a negative sign, and displacement as a positive sign, which makes a lot of sense. I mean, we're lifting it up, but gravity's still pulling down against it. So the work done by gravity is negative. And you don't think about it too much because, well, you're not gravity. But that's pretty much how it's going to work. That as this increased, in order to increase GPE, we had to have the gravity to do negative work on the block. Well, that's a constant force. Let's look at our famous case of just a spring that obeys Hooke's law. Starts in an equilibrium position, has a spring constant of K. When it's here, it has no potential energy. When we stretch it out, it has potential energy. We stretch it out some distance x naught, the potential energy, as long as it obeys Hooke's law, as long as it follows force equals kx, is going to be 1/2 kx naught squared. So as we stretch it out, the work done by the spring, well, the spring, remember, is trying to pull it back to equilibrium, so it has a positive force. And this is a negative displacement. So a positive force times a negative displacement is going to mean that negative work was done by the spring. The spring got the short end of the stick here. It actually gave something up in terms of its work. But the potential energy, since now we have these stretched out more and they want to snap back to this equilibrium position, that potential energy is going to be gained. Makes sense. If we work the opposite way, we should get a similar type of relationship. So for the potential energy now, we're going to start from this cleverly rearranged picture where we start from the stretched position where it's here and let it go back to equilibrium. Well, it's obviously going to go faster here. Again, the old energy is conserved. We're going to end up with some kinetic energy here. It's going to actually be moving. And then it's going to compress the spring and all that kind of good stuff. But if we look at releasing this spring, the work done by the spring, well, the spring wants pulled back to equilibrium. Up to this point, it's a positive force. And it's going in a positive displacement. So we're going to have a positive work done, which makes sense. Force times displacement, assuming force is constant, will give us work. Even if force is not constant, the sign didn't change here, so it's still an okay analogy to use. But the potential energy, it's lost. There's less of it than it started with, which, again, is reasonable. It gets to here, it doesn't have any potential energy. So in terms of work and potential energy, you've probably already figured out the relationship. When an object's potential energy increases, the work done by the force necessary for potential energy is negative, in an equal amount. And the opposite's true too. If the potential energy decreases, becomes more, if there's a loss, then the work done is going to be positive in an equal amount. It's sort of a conservation of energy thing. So work's going to equal whatever the opposite of the change in PE. Or if we want to write it in an integral form, the change in PE is going to be the opposite of the integral of force with respect to the displacement. I could put 0 to s prime or something like that, but it doesn't really matter that much. In the problems today, all you're going to do is just take a bunch of functions for force and integrate them and figure out what the change in potential energy is. Now, that change in potential energy could mean a loss in kinetic. It could mean a gain in kinetic. That's what your job is to figure out today. And